So now let's look at the special cases of the conservation of mass. Okay, so I usually call this CO mass. Okay, some people call COM. I sometimes do that as well, but be careful. Conservation of momentum, that also can be COM. I will actually have three special cases. Okay, the very first one is I'm going to call this a steady flow. Okay, and I covered steady in module number 4. There was a segment unsteady, steady, 1D, 2D, 3D. I'm gonna repeat over here, but basically if I have something as a function of time, well, it is not. Okay, so it is not changing over time. So now let me go back and show you my equation over here. So what do you think is going to happen to in here? As I mentioned, this is the time rate of change of mass over the control volume. Can I have this changing over time? The answer is no. I get myself del t of 1, 2, 3 control volume rho d volume will be equal to 0, and hence from here first term drops out. Look at it. First term drops out, so I'm all left with this. So this needs to be equal to 0. So okay, let's write it. Double integral over the control surface rho v dotted with n dA is 0. Okay, so and also just a few minutes ago what I did was I called this m dot inlet and m dot exit. Look at it. So I can simply call this whole thing as this as well. M dot exit minus m dot inlet is equal to 0, or I can call this m dot n exit is equal to m dot inlet. The second one is I'm going to still have steady plus constant density. What I want to do here though is before I go ahead, you may see in some books or some professor notes but where they're saying that this is incompressible. That is technically not correct. Okay, I'll show you a difference. So incompressible means that I cannot really compress it, right? So if I have a system like this, right? If I have a density 1 over here and density 2 over here, I cannot compress this anymore. I cannot compress this anymore. So this is going to be a constant value and this is going to be constant value. But this incompressible doesn't mean or say that this density must be equal to this density. Okay? I want you to be aware of that. The reason why I bring this up is if you see incompressible, they mean to say the constant density. That's quite all right. Okay? With this steady, I start with this equation. Okay? And with density being constant, look at this equation. I'm saying that the density is constant. Can I take that out of the integral? Oh yeah, I sure can. Let's do it then. So then it becomes density, now double integral over the CS V dotted with n dA is equal to 0 this time. So this is a case where we have this as basically this is A times B is equal to 0. What does this mean? Either A is equal to 0 or B is equal to 0 or both are 0. A is equal to B equal to 0. Now the question is, does it make sense to have my density 0? So what that means is I have an arbitrary space and inside of it I don't have any mass. I don't have any molecule. I don't have any particles. That's the definition of vacuum, right? In real life we don't have that. So for that reason density cannot be 0. The only opportunity that I have is this B0. What it means is I look at it, so double integral over the control surface V and dA is equal to 0. Okay, so similar to this over here where I call this m dot, right, over here, we have another name. This is called the volumetric flow rate, okay, and it's abbreviated as Q. So the Q dot exit minus Q dot inlet will be equal to 0. I'm just following the same, right? Look at this, m dot exit, now it's Q dot exit, okay? And then if I basically equate them, you can see I get myself Q dot exit is equal to Q dot inlet. So that will be my final formula for the steady and constant density case. Let's write over here, this is volumetric flow rate. And sometimes in the books and all, I see people just simply refer to it as flow rate. That's not perfect because there is also mass flow rate, right? This is called, let's actually go ahead and write this over here as well. This is called mass flow rate. When people call it flow rate, they mean to say this, okay? They mean to say this, not the other one. And the third special case is I'm still gonna have steady. I'm still gonna have constant density. And I will also have uniform flow. So the question here is, what is uniform flow? We didn't really talk about it. So let me draw my system again. So I have a nozzle. I keep giving the same example, but whatever. So I have an inlet over here, and I have an exit over there. I have my control volume that I selected. Okay. So what is going on over here is I have an inlet, I have an exit. But what does uniform flow means? And I sometimes see this as a mistake. I ask this very question to students when I teach in class. They say velocity is constant. Velocity here is equal to velocity there. Okay, that's not quite right. Actually, well, you'll find out that that's not even physically possible. Here's what it means. Velocity is a vector. Vectors are defined at a point, not at an area. Okay, so how am I going to translate when I say the velocity in here is equal to, let's say, 2 meters per second? Okay, but then I'm multiplying this by area, right? Take a look here, up here. V times A. So I'm multiplying something that's defined at a point with an area. I'm generalizing this velocity is everywhere over the inlet is 2 meters per second. Take a look at over here. So this will be, let's say, 3 meters per second. You will see why it needs to be larger soon. So it's like this, okay? And it is uniform. So you can see this is uniform, this is uniform. So both doesn't have to be uniform. I can have one uniform and I can have one non-uniform. Now take a look over here. Can I take this V outside of the integral? The answer is yes. V is a number. They are not the same, but I'm evaluating one by one. At the exit, I call it positive V. I call it at the inlet, negative V, right? And 0 otherwise. So this 2, can I take 2 out of the integral in this particular case? Oh yeah. Can I take 3 out of the integral? Oh yeah. Okay, let's do it then. V dotted with n goes out of the integral, and I have double integral over the control surface dA. That is equal to 0. What is this? In order to explain that to the students, I do a technique, say this, what is dx? Because sometimes I don't hear positive responses. So this is x. We kind of know that already, right? Okay, so over here then, area is like dx dy, right? So what is this when I ask? Or you can do this, if this is independent of that, you can call it like that, right? So this is x, this is y. What is x times y? Well, that's area. Okay, you just told me the answer, it is area. I'm going to go over here and call this is my area. But remember, there needs to be a summation sign, because I may have multiple inlets and multiple exits. If that's not the case, I have one inlet, one exit, just like I'm drawing over here, you're going to have to differentiate or sum. Summation over the, let's call this inlets, and I need to put negative sign in front of it. That will be V n inlet, A inlet, plus over the exits, V n exit, A exit, will be equal to 0. And remember, I'm not doing anything new over here. This is Q dot exit, this is Q dot inlet. And if I rewrite this, you can write two-way. Q dot exit is equal to Q dot inlet, because I can move this term to this side of the equation. Okay, so that's option 1. So this is option number 1. And option number 2 is writing it like this. Summation over the inlet, V n inlet, A inlet, will be equal to summation over the exit, V n exit, A exit. Okay, so this is the second option as well. This is much more direct as opposed to this. Okay, are there only 3 special cases in real life? Oh no, who said that? How can I classify things into three categories only, right? So now, but before closing it off, I want to also highlight something called Vn. Why did I call n over here? Well, the origination is v dot n, right? Just to remind myself that the origin was v dot n, okay? And this is a different distinction, okay? And one other thing that I want to note before I close off the segment is sometimes I see students making mistakes this is a scalar equation, like 1 is equal to 1 or 5 minus 5 is equal to 0. It's not like a vector where it has components in the x, y, and z, okay? So do not get mistaken over there. You're not going to have sine or cosine of the velocity in the x and the y, etc.